All right, let's now talk about tree-selected machine learning techniques. The first one is decision trees. After that, we're going to talk about naive Bayes. Finally, we're going to talk about the latest state-of-the-art neural networks, also known under the name of deep learning. So what's the decision tree? Basically, this is a tree where we want to classify an input. An input could be a sentence or a string, and we go through the tree, and at each node in the tree, we're going to make a decision. This could be, for example, be a binary decision. Depending on certain feature values. For example, let's assume we want to classify a name that is a sequence of characters into whether this is a female person or a male person, and at least for European names, we can guess that based on the form of the name. For example, a name like Marta would be a female name, whereas a name like Carl would be a male name. So we could go through the decision tree and make and branch out depending on the feature value. So for example, we could say it's the last letter a vowel. If this is the case, then we check whether the last letter is indeed an O, and then we check whether the length of the string is 3. And if so, we say this is yes. This is a female name, otherwise it's a male name. And I'm not saying that these features here now actually are very meaningful for our task, but those could be could be a tree that is learned by our model. And we assign the labels, as you see here, at the leaf nodes. Now, the interesting thing is, how do we decide which feature value we're going to use at each input? And we're going to explain this in the next slide. So again, consider our example of gender identification, where we have names and we have our training data, which consists of like the labels male, female, and associated with that, of course, is a particular string value. So for example, Marta would be female, Carl would be name. So we could check a certain feature, such as whether the last letter is a B, and then we could check what kind of how that feature value splits our data, right? So we could say, okay, you see, if the last letter is B, then our data is then like 50% of the instances are a female and the other 50% are male. If this is not the case, there's a certain other distribution. Now, maybe we want to choose a feature that splits our yes and no decision into different groups. And maybe the better the split is, the better is this feature at the current leaf node. And in this case, we would say, okay, we prefer this split because the two sets now are better separated and better organized. And there's a certain way to formalize this idea using entropy, but we're not going into that in the concept of this course. Good, so this is already a brief illustration on decision trees. What are advantages? They're simple to interpret, and this is one of the main reasons that they have actually been reused in the last couple of years. So they were invented a long time ago, in the 80s, 90s of the 20th century. And they weren't so popular in the last 20 years, let's say. However, the fact that they are easy to interpret and easy to read for humans, and they are also similar, their structure is also similar to human reasoning, is something which is very appealing for them. So that is a big plus for them. And they're especially useful to learn models for data which can be hierarchically categorized. Like exactly, a tree makes such a hierarchical classification. So if the data is already has already a similar underlying structure, then this is probably a good technique for such data. On the other hand, we have the problem that the amount of training data in the lower nodes is quite small, and so because a split decision is made at every node, so the lower we come in the node, the less training data do we actually separate there, and we need to make sure that we do not overfit and do not model particular idiosyncrasies of the data. So what could typically happen is at the lower nodes, we got very idiosyncratic data set properties, like might be some noise in the data set, and we may fit this noise actually in the data set because we model and we mimic this data set in particular, and this prevents us from doing a good generalization. And also there's probably a certain order on the features, even if, and this is enforced by the model, even if the features are independent of each other. And in general, also a disadvantage is also that the model does just not perform so well in practice. So this is also one of the reasons why the model hasn't been used so much. So let's talk about our second model, which is naive Bayes. And now how does it work? So, and we need a little bit of math for this classifier. Naive Bayes classifiers make use of every feature to determine a correct label. And it starts out with prior probabilities of each label. Assume we have like a classification problem with like n labels, and we have a prior probability. How likely is it to be a male name or a female name? And this prior probability is based on the frequency of each label in the training set. So we got a prior probability for each label that we have in our classification task. And then we have features like, for example, the occurrence of certain words. So does the word cat appear in this text? So this could be a feature. And we combine the contribution of each feature with the prior probability to get the likelihood of each label. So for all features, we have this conditional probability of the feature given the label. And just to introduce a little bit of math notation, in general, the conditional probability of A given B is defined as the joint probability that A and B, like these are two events happen, divided the probability that B occurs. So the probability of being criminal, given that you are female, is the probability that you are female, and criminal divided by the probability that you are female. And what naive Bayes is then choosing, like for each input value, an input value is an instance to be classified. So this could be, for example, be a sentence or a string. We define our features on this input value, and then we choose the label that maximizes the product of the prior probability of this label multiplied by the feature contribution to the label, and this is the conditional probability of the feature given the label, and we multiply this over all features. So this is the course outline of naive Bayes. Now let us go a little bit into the structure. Why does it have this particular structure? So naive Bayes critically makes an assumption, which is a conditional independence assumption, and which says that given a label, all features are statistically independent of each other. For example, words, if the features are words, are independent of each other. And let us look into a motivation for this. So when we think about probabilities and joint and conditional probabilities, well, what we would actually want to maximize is something like this. Given the features, so we have an input, we have feature representation of the input, we want a label that has maximum probability given the feature. So this is actually what we want to maximize, right? Given the feature representation of the input, what is the most likely label? Is this male? Is this female? Is this a sports article? Is this a news article? Now let's assume for simplicity we have only two features, so we write it in this way. We want to maximize the label that has the highest probability given feature 1 and feature 2. Now let us rewrite this formula in such a form using a rule or a formula which is also known as a base formula in the literature, and it's actually pretty simple. So it says that this probability of the label given the events or the features F1 and F2 can be written as the probability of the label multiplied by the probability of the features given the label. So we rewrite this here, and then we also divide by the probability of the feature 1 and the feature 2. So why is this the case? Actually, you can calculate this out just using the above definition that we had before. So we have like P of A and B divided by the probability of B is the conditional probability. So if you plug in this definition here, what you will see is that if you multiply this with this, then this goes in the denominator, and we're going to have P F1 multiplied PF, the probability of F1 and F2, and the label is in the denominator, and in the enumerator is the probability of the label. This cancels out. So we have that PF1, PF2, and the label, comma. So comma and the word and are like synonymous in this mathematical notation, stays on the top, and we divide by F1 and F2, and this is exactly the definition. So this formula here is pretty simple to derive. And now if we want to maximize the label given the feature, then this term here becomes a constant. So we don't really need this term here, because this is not something to maximize. This is something that is given. So we only have those two terms left here, right? So those two terms are left. Now the naive Bayes assumption is this conditional independence assumption that feature 1 and feature 2 are independent of each other given the label. So under this independence assumption, we have this equality PF1 and F2 given the label equals the probability of F1 given the label times the probability of F2 given the label. This is under the conditional independence assumption. This assumption is not true, so that we cannot assume such independence, but using this assumption, we can actually get a nice and simple formula that is easy to compute and easy to calculate, and this is tractable, and therefore that makes our algorithm and our model simple. Good. So actually, based on this naive Bayes assumption, we can write the probability that we actually want to maximize, namely the label given the features, is written as this independent, as this product of independent terms, the label multiplied times the feature given the label multiplied over all the features. So the example is, let's assume we have an input document and our features are the words. So we identify that dark occurs in the document, football occurs in the document, etc., etc. Want to estimate the probability that this document is about soccer, we would multiply the prior probability that the document is about sports times the probability that given that it's sports, we observe the word dark, given that it's sports, we observe the word football, etc., etc. And as I said, it's unreasonable to assume that all features are independent. If football occurs, it's more likely that goal also occurs. So there's certainly a dependence among those features. However, this makes our algorithm tractable. And also, while the algorithm is therefore suboptimal. It still did work quite well in practice for some time. And now these slides were originally made a couple of years ago. And it says that naive Bayes is often used. I would harshly debate this. It's not at all often used. I know very few people, if anyone, that still uses naive Bayes, but for some time it was a reasonable baseline. However, I recommend you not to use it. Better than naive Bayes is even the decision tree, because it gives this aspect of interpretability, which has become very important in the last couple of years. Now let's make a naive illustrating example of a concrete example of how we could do document classification with naive Bayes. Assume we have 3 labels, like a document could be about automotives, it could be about cars, it could be about sports, or it could be about murder mystery. So this is like, it could be fiction, criminal, right? Criminal fiction. So these are the 3 categories, 3 labels that we have. And let's assume our probability says most documents are about cars. So if we get a new document, we would start with automotive in the top right corner. That's our prior assumption that this new document is going to be about cars. Then let's say our first feature. So we only have 2 features, and one of those features being dark. So we would start from this probability, and then because dark is somehow indicative of murder mystery, then we could go in the direction of murder mystery. And then the second feature that we have is the word football occurs in the document. So we would strongly go into the direction of sports. And note that this is just a naive illustration, but it may give you some intuition of what is going on.